Welcome, and this one, let's take a look at finding limits at infinity by dropping subdominant terms. So what does that mean in practice? F of x, let's see, is 1 over x squared and then plus x. We would like to know, in terms of a limit, when x goes to positive or negative infinity, which of the terms in the bottom, say in the denominator, has a bigger impact. So to do that, take a look. You have to compare them somehow. How do you compare them? You just graph them individually. Take a look here. So if I graph x squared, that looks like this. It's a parabola. And then graph the other term there, which is just x by itself. Just graph them separately so you can understand the relationship between them properly. When I do that, notice that on the horizontal, it's 0, 1, 2, 3, 4, and on the vertical, it's 1, 2, 3, 4, 5. So scrunch it over this way and then scrunch it down a little bit more. And you can already tell that clearly the x squared term dominates the green one. In other words, look, at 2, for example, you see the green one has a value of 2, but the x squared part has a value of 4. At 4, it's already hard to see. So what I'm going to do, I'm going to pull this down. And you see when x is 4, then x has the value 4, whereas x squared has the value 16, and you see that 16 is 4 times as big as 4. And then so on and so on as x gets bigger. Why does that make a difference, understanding the relationship? Because what it tells you then is the following. You can write the limit as x approaches positive infinity of 1 over x squared plus x would ultimately, because x squared gets so much bigger than x, like the graph suggests, this would be the same as writing the limit as x goes to positive infinity of the following. 1 over just x squared. In other words, I just dropped the x term for the reason that the graph expresses. Take a look. If you graph, in other words, the following, take a look. 1 over x squared plus x, that looks as shown here. And if we graph 1 over x squared this way, you see in the limit, when x goes towards positive infinity right here, that's when x is big, in other words, you can't really separate them out anymore. You see they look about the same, 1 over x squared plus x and 1 over x squared, in other words then, for the purposes only of taking a limit, are the same. And in both cases, as you can see from the graph, this approach is 0. So the value of the limit is 0. You cannot use this approach to dropping, for example, subdominant terms when you are close to 0. So what I mean by that is the following. Look carefully here. You see that around 0 itself, so this is the space there, say from 0 to about 3, you see that the graphs are clearly separate. In other words, 1 over x squared plus x is quite different from 1 over x squared, when x is a small value like 1 or 2, maybe even 3, and so on, okay? But when x is large, then for the purposes of doing limits, you treat them equivalently. So having said that, let's take a look at additional examples. So you can see how this actually simplifies things. So the limit as x goes to positive infinity of the following. X squared plus x, and then here x cubed, say, plus, and then 4x plus 5. When you look at this, it might be difficult to decide how to find the value of this limit, naturally enough. It's kind of complicated looking. So what you can do is the following. Take a look. Look at the graph here. If I graph the original, then the graph will tell me what the limit is, but the graphs are not always permitted or available. And I can tell the following when I look at this graph, that when x goes to positive infinity, you see the values of the function drop off to 0. I hope you see that in the graph. So x is going this way. It's 2, 4, 6, 8, 10, 12, 14, 16. You see that the values of the function get closer and closer to 0. What I could do for the purposes of doing the limit is drop the subdominant terms. So what does that mean in this context? It means the limit as x goes to positive infinity. And what I can do is, relative to x squared, x is much smaller when x is a big value. So I could say just x squared in the top. In the bottom, relative to x cubed, 4x plus 5 is much, much smaller. X cubed is a cubed quantity. 4x plus 5 is a straight line, that part of it. Which means the x cubed dominates the 4x plus 5. So what I can then say is that this just becomes this right here. Look very carefully at this new limit form. You have to understand this. If I do x squared over x cubed, you see around 0, so where it's 0, for example, and 2, up to about 4, the graphs clearly look different. Not relevant for our purposes. What matters is that when there's 6, 8, 10, 12, 14, 16, 18, and so on, when you hit those higher values, then they look about the same. You cannot tell the graphs apart anymore. That's what's relevant for when x is a large value. All right, and the same thing then at the next stage, limit as x approaches here, positive infinity, and then you do the following here. You have to cancel off on x squared between top and bottom, so it would look like this. X squared times 1 over x squared times x. The x squared parts are the same between top and bottom. You can cancel them off, and you end up very nicely with the limit as x approaches positive infinity of 1 over x. We have seen this limit before. Perhaps you remember this value is equal to 0. Look at that last stage in the graph, in other words. Take a look. I'm going to do this one in red. Just graph 1 over x. And if you look very closely, right here, where it matters is here. The values are about the same as x goes towards positive infinity. So I began with this pretty complicated looking expression, x squared plus x over x cubed plus 4x plus 5. I dropped x and 4x plus 5. That gave me this. And I saw by using my graph that when x goes to infinity, this here and the original can be used interchangeably. Then I just did a bit of algebra to cancel off the x squared, and I got it down to 1 over x, which is one of the most elementary things that you look at first when you're doing limits at infinity. And that is it for this one. So thank you, friends. I'll see you in the next video.